Hello, my name is Thorsten Höffler. I'm a professor at ETH Zurich, heading the Scalable Parallel Computing Lab. Thanks very much to Hal Finkel to organize this panel at the Supercomputing 2021 conference in a hybrid setting. Here we're in the online version. I was actually in the room while this was going on, but multiple requests came to me that the quality at the conference was not so great. So thus I'm giving this quick overview of my panel opening speech, or little speechlet, I would call it, to make the point that data movement is all you need going forward. Really, don't worry about flops anymore. So what is the most computationally intensive, the most matrix multiply workload you can imagine today? It's really deep learning. As we've seen, many vendors implemented tensor units, or these are really just matrix multiplication units, but tensors sound much fancier. And these matrix multiplication hardened in hardware provide a huge speed up for deep learning workloads. In fact, going to one of the most computationally expensive workloads today, transformers in the form of derivatives of BERT, but really going to extremely large scales like GPT-3 and Gopher from Google and much larger frameworks. We can actually see how expensive it is to train these about 200 billion parameter models. So for OpenAI, it was guessed that it's about $12 million to train that one model. So it's actually quite a lot of an investment. And now the question is, of course, this is highly optimized, because if you pay $12 million to train a single model, you better make sure that your code runs efficiently, because if it runs only at 50% efficiency, then you could save $6 million. So that gets you a lot of performance engineers to hire to just improve the quality or the performance of your code. So now looking at what is the share of operations in this code, we see it's really 99.8% tensor contractions, which are essentially mappable to matrix multiplications. So 99.8% of the floating point operations can be executed by matrix multiplication units one way or another. But as we see, it's only 61% of the runtime, because these units are so fast. We're seeing an interesting case of Amdahl's law, and we actually see that the optimization of those tensor contractions leads to new bottlenecks, such that the 0.2% of the floating point operations actually make about 39% of the runtime of this code. So this is all data movement. This is all just moving the data across the chip and marshalling it into the right form to be ingested either by the matrix multiply units or actually just ingested by some kind of very simple calculations, element-wise calculations, or things like softmax. And we can see that actually, if we worry about this 0.2% of the flops, we can get a significant speed up for a Birch large implementation on a single V100 GPU. So we can actually get 30% over PyTorch and even 8% over a manually tuned framework. I don't have enough time to explain this to you, but what we can see, if we would have applied this to GPT-3, then we could have saved $3.6 million just for the single run. So the PhD student who has done this, Andrei Ivanov, and under the guidance of myself and various lab members, would have been rich. But yeah, well, unfortunately, that came a bit too late. But you should watch his video on YouTube and to just learn how he did this. So it's a full research talk there. You find the URL at the bottom. And again, I don't want to steal his thunder here. You can also read his paper. It's on arXiv, as well as appeared at MLSys. Was one of the best papers at this conference. Okay, but now we are in 2021, and I just showed you that really data movement, even for highly compute-dominated workloads like transformers or deep learning in general, is extremely important to take care of. But now let us go back in history to 2011. In 2011, from the abstract of the Exascale Computing Technology Challenge paper, we see, in particular, they will need to manage locality to achieve performance. So in 2011, John Schalf and colleagues actually pointed this out very clearly in the abstract, that we need to worry about locality mostly. So 10 years ago. So what happened in those 10 years? Unfortunately, not much. It's very shocking. It's clear that we need a completely different way of thinking, teaching, and arguing, yet we are still counting flops. And I think the problem lies that really we are growing up with this flop-centric or operation-centric viewpoint. Because how do we teach complexity theory to undergrads? Well, I'm partially guilty myself, because what you do, even in sorting, which is all data movement dominated, we count the number of comparisons. If we talk about any computational workload, we usually count the number of operations. We do not really teach data movement at the university level, Because I/O complexity is extremely hard. Because we don't even know how well we are using the memory for most of the algorithms. We have very tight computational complexity in terms of operations bounds, but data movements bounds are much harder to achieve and are rarely actually taught in practice and rarely used in practice. So what we do very often is we look at what percentage of the bandwidth do we achieve, for example, in roofline models. But roofline models are absolutely useless if you're using the bandwidth inefficiently. If you're saying, oh, I achieved 99% of the memory bandwidth, but I'm using an extremely bandwidth inefficient algorithm, for example, a matrix multiplication without tiling. If I don't tile, I can easily achieve 99% of the bandwidth, and I will be at the top of the roofline. I will be perfectly happy, but my code is absolute utter junk. So how do we deal with this? Well, we introduced a new metric a couple of years ago that we call memory use efficiency, which you can see is kind of amendment to the existing bandwidth peak utilization metrics. It's a bit more complicated to compute because now you need two things. You need to measure two things. One is how efficiently are you using the bandwidth. This is the second one. That's the easier one. That's why I start with it. And the first one is we need to understand how efficient is. The second one is how efficiently are we using the bandwidth of a specific device. So it's really the measured bandwidth divided by the peak bandwidth. That's what the roofline model measures. But we need to multiply it by a factor that measures how close is our algorithm actually to the I/O lower bound. So how efficiently, algorithmically are we using this? And this is where it gets complicated. So this is where the rubber hits the road and really we need to develop a whole lot of new theory. So it does work in practice. In fact, we had some successes at the supercomputing conference, but I would actually like Alex Eichen, who gave the keynote at the Charm++ workshop a couple of weeks ago. I would like him to speak because he was pointing towards our code, the Cosma code, as state-of-the-art for high performance on very large-scale CPU-based systems and also very fast on GPU-based systems. And for this code, we purely optimized in a data-centric view. And we actually even got the SC19 Best Student paper because that view is fundamentally different from what people have done for matrix multiplication for the last couple of decades. Well, not fundamentally different, and people have started looking at this, but we have actually done the whole connection between deep theory, trying to understand what is the I/O optimal solution, with practice, really implementing the fastest matrix multiplication for these particular machines that we worked with. We extended it this year at the Supercomputing 21 conference, where we are virtually at right now. And this is a talk that's appearing on Thursday, and it'll also appear on our YouTube channel at the Scalable Parallel Computing Lab in case you had to miss the conference or you didn't register for whatever reason. So if there was just a tool that could help you to understand the data flow of an application, well, that is actually another thing we are working on in my lab, data-centric Python, where we transform Python codes into stateful data flow graphs, where we can actually look at the data flow. As you can see here, it shows you as you're hovering over various connections, so they're arrays. It shows you the data movement, it shows you the computational intensity, and you can now really understand the data movement of your code, even for relatively complex codes. Furthermore, there is an integration for performance engineers where you can look at the code on the left side. You can apply transformations automatically that optimize data movement, as we are seeing here. So a loop tiling transformation is performed. It's a splitting transformation, but loop tiling also works in this framework. And it's really the click of a button where we can see, we can immediately see the new data flow. The code is automatically generated, and you can even run it very conveniently. Now that was a loop tiling. In order to check what your performance really is. So you don't need to even change the source code in order to improve data flow in your code. So with that, I would like to close my talk. Thanks again, Hal, for inviting us, and I'm looking forward to the panel discussion.